So for number 1, we're asked to find the 3 missing dimensions, x, y, and z. And what we have here is we have this line across here that cuts this angle into 2 60-degree angles. That's what we call an angle bisector. But what else do we notice about this triangle? Those 2 lengths are the same, which makes it an isosceles triangle. So if we have an isosceles triangle and we have a line that bisects that angle between the 2 equal sides, what else do we know about it? It cuts this other side in half, yep. And it makes that a right angle. Perfect. If it's an angle bisector, it's also an altitude and median line. So that means Z is going to be 8.66, very good. X is going to be 30 degrees. 60, 90, 30 adds up to 180 for these 3 angles. And we can find Y. I'll do a little bit of a shortcut. It's actually going to be 10 squared minus 8.66 squared. What did I use minus there? Because we know the hypotenuse, what we're looking for is one of the legs. We're going backwards. That ends up being 5. Y is 5. How many of you had all 3 of those answers? Good deal. Number 2, did anybody get all 3 of those? Okay. Well, we know that the 5 relates to the Y. We know that 5 also relates to the X. We know that 12 relates to the Z. Now we know that 12 also relates to the X, depending on which triangles we're looking at. So, and we also know that 13 relates to the 5 or the 12, depending on where we're looking. So I'm going to take the big triangle and I'm going to relate it to one of the small triangles. I want to relate it to the one on the left or the one on the right. You guys pick. The right, okay. So I am going to start out with the 13 in the big triangle. What side of that right triangle does the 13 relate to? The 13 is the hypotenuse of the big triangle, right? On the right triangle, 12 is the hypotenuse. So 13 relates to 12. Now I'm going to pick one of the sides in the little triangle. I'm going to look for X. Now that's in the same smaller triangle, the one with the 12, so that goes on bottom. What goes above it? What relates to the 13? Or what in the bigger triangle relates to the X? Be the 5, the smaller leg, right? Okay, so we cross multiply. 12 times 5 is 60. Divided by 13 is 4 and 8/13. That would be X. To find Y. Actually, sorry, we'd have to find Z if we're using that triangle. So we still got 13 relates to 12. Z is the longer leg of that triangle. So that's not going to, yeah, it is. Z is going to relate to, hold on here. Yeah, Z can go in there. Z is going to relate to which side of the big triangle? It's the longer leg of the little triangle. What's the longer leg of the big triangle? 12. So Z relates to the 12. So now we cross multiply and divide. We've got 12 times 12 is 144 divided by 13. 11 1/13. Yep. So Z is 11 and 1/13, which makes Y 1 and 12/13. What do you think? Any questions out of your homework you want me to go over? Which page is that? 300. Number 21. Ah, missing angles. This one ought to be fun to draw out. Oh, so we have right angles there. Given that this is 60, 124, 50, 50, 90. This is Y. This is X. X is actually not too hard to find, because X is the same as this distance all the way across here, right? So if I know this piece, I just add it to 50. If I call this here A, I can find A rather easy. 60 squared plus 124 squared equals A squared. So we'll do the second square root. Oh, square root of 60 squared plus 124 squared. 137.75. So I add that to the 50, makes X 187.75. Next, to find Y. Since Y goes at an angle, what we usually try to do is try to create a right triangle using a horizontal dimension and a vertical dimension. We already have that horizontal dimension is 187.75. That vertical dimension is 40. Very good. The just difference between 90 and 50. So it's going to be the square root of that previous answer squared plus 40 squared. 143.44. That did not work out right. No, it did not. Let me try that again. 187.75 squared. Oops, yes I did. $191.96, that's better. So 191.96. That should be it. Any others? Okay, some of you are still working on the quiz, and that's fine. If you'd set it aside, we'll finish it up later. We're going to take a look at some of our new material. So, as some of you saw on the packet I hand out, we're going to start talking about circles today. So you might be wondering, when are we going to get to the trig? Well, circles are actually the basis of trig. When you think of trigonometry, most people think of right triangles. And that's where it mostly gets used. But that's not where it came from. Trigonometry comes from a circle and parts of a circle. So we'll start out with just a review of the basic parts that we already know. If you pretend that looks like a circle. The most basic part of the circle, of course, is its center, which is just a location. And then from that center out to the edge, that distance is called a radius. And actually, those two pieces, a center and a radius, completely define a circle. It is simply a single point, and it's actually the technical definition of a circle is all points located a certain distance from a given point. Now then we have any line segment that has its endpoints on the circle is called a chord. Very good. A chord that happens to contain the center of the circle is called a diameter. Brings us to our first relationship. The diameter is equal to 2 times the radius. And then we have distance around a circle is called the circumference. And of course, we have another relationship. The circumference is equal to, well, pi times diameter, or 2 times pi times radius. Right? 2 times radius is the diameter. So those are the basic pieces that we already know. And there are some that we learned during last semester. One of them looked like this. What's that called? It's a sector. A sector is defined by this thing here. That is referred to as a central angle. Remember, it was that angle, that central angle that we use to find the area of a sector. Then, of course, there's this thing here, which is a arc. An arc is just a piece of the circumference. And we talked about arc length last semester a little bit too. The length of that arc is related to that central angle as well. If we take a chord, the piece that's cut off outside of that chord is called a segment. That was the one that we had a lot of fun finding. Remember, you have to find the area of the whole sector and then subtract out that triangle. And that's really probably about it as far as things that we already knew. So let's look at some new things that we don't already know. What does the word tangent mean? Well, just the word tangent. Connected? Kind of. Touches or next to, right? A tangent to a circle touches it at exactly one point. Technical word for tangent is it touches but never crosses. So two lines can't be tangent unless they're the same line. They cannot touch and never cross. Curved surfaces can have tangents, like a circle. One of the things that we'll learn about a tangent, of course, is it has this very special relationship with that radius. That relationship is always at a right angle. Secant means to cut through. A secant line cuts through the circle in at least one spot. Now, in most cases, it cuts through it in 2 spots if it continues on, but at least one. we saw the central angle. But there's another very special angle called the inscribed angle. Inscribed just means the vertex is on a circle. So there's something called inscribed polygons, which means all the vertices, all the corners are on the circle. Both of these the central angle and the inscribed angle, are special cases of something called an interior angle. All four of these angles here would be called interior angles. So in fact, there's 6 interior angles that I've created up there. And then the final angle that we're going to look at for today, if I have a tangent line, an angle whose vertex is at that point of tangency is called a tangent angle. So all of these different angles and all these different lines and stuff are going to have there's actually a lot of math that goes on in a circle. In fact, one angle that I should put on here, I'm going to put it over here just because I'm getting a little proud of another one. This, of course, would be an exterior angle. Now, what are both of these green lines that I just drew? What are those called? They're both secants, right? Because they cut through the circle. So a double secant exterior angle is one type of exterior angle. There is what do you think that would be called? This tangent secant or a secant tangent. And then there would be a double tangent, right? And again, there's going to be a lot of special rules that we'll look at for all of those. We want to now focus on arcs for a little while. One thing that we saw at the end of last semester. If I have a circle with a radius of 12 inches and a central angle of 50 degrees, if I want the length of that arc, what is the first thing I find? Circumference. 2 times pi times 12, which is 75.36 inches. And then how do I find that arc? The arc length is that whole circumference times the fraction of the circle. That central angle tells us that's 53/60ths of the whole circle. Giving us 10.4667 inches is the length of that arc. Any questions there? Is that pretty familiar? So now, let's say that in this circle, I have chord AB. And chord AB is 14 inches long. I also have chord CD. Chord CD is 14 inches long. Now here, arc AB would be listed like that. AB with that kind of curved, the arc literally above it. What can I say about arc AB and arc CD? They're the same length. They are cut by equal chords in the same circle. It's very important it's either the same circle or a circle with the same radius. Because if they have the same radius, they're identical circles, right? As long as they have the same radius, if the chords are equal, the length of the arc will be equal. And vice versa. If they have the same arc length, the chords that cut across from endpoint to endpoint of that arc will also be equal. Similarly, let's call this arc EF. What can I say about the length of arc EF? 10.4667, right? Because if I call this arc GH over here, they both have a central angle of 50 degrees. And again, those are in the same circle, but any two circles with the same radii. We could say that those arcs are the same. So that's two things that we can use to create equal arcs. We have the same central angle. Obviously, we have to have the same radius, either way. So we have the same central angle, or we can have equal chords. Two ways to cut equal arcs. For now, we're going to call that good enough and give you guys page 305 in your new packet. Now brace yourselves, it's the big one. 1 through 8. Have mercy on you guys. I've been giving you a lot of homework lately. Even I feel guilty after.